today I'm going to go over the kinetics topic, which is on paper 2 of the new chemistry A-level specification. So the kinetics topic is quite simple really, consists of the collision theory, rates of reaction and Maxwell-Boltzmann curves. So we'll start off with the collision theory. The collision theory basically states that for a reaction to occur, there needs to be a sufficient energy during the collision. So the minimum energy required is called the activation energy. Okay, so next we move on to reaction rates. The first factor is concentration. So increasing the concentration of reactants means that there are more reactant particles, which means more likely collisions. If there are more likely collisions, this means there is a higher chance of a successful one. Next we have pressure. So when you increase the pressure, there are more particles in a set volume. This means that particles are forced closer together. And so more collisions equals more chance of a successful collision. Next we have temperature. So increasing the temperature means that particles will gain kinetic energy. And so they collide more frequently and often with more force. If they collide with more force, this means there's more chance of sufficient energy, also known as the activation energy, and so increases the chance of a successful collision. So next we have surface area, and this only really applies to solid reactants. So what this does is it increases the number of particles exposed to the reactant surface. And so this means more frequent collisions, which equals more likely a successful one. Last but not least, we have the presence of a catalyst. So just refreshing your memory, a catalyst increases the reaction rate without being used up. So how catalysts increase the rate of reaction is that they provide an alternative reaction pathway of lower activation energy. This again leads to more chance of a successful collision because particles don't have to have as much energy. Okay, so you can show the rates of reactions on a graph with time on the x-axis and volume of product on the y-axis. Okay, so for this particular reaction, if we use smaller molecules half the size, our graph would change and it would look like this. It would look like this because you're using smaller molecules, so there is a larger surface area and therefore increased reaction rate. So reaction rate is change in concentration of product over time. So in this case, steeper the gradient of the graph, the faster the reaction rate. But then you can see that both graphs plateau out. And this is due to the fact that all the reactant has reacted and no more product can be formed. Okay, so next we move on to the last section of kinetics, which is Maxwell-Boltzmann diagrams. Okay, so in a sample of a gas or a liquid, the molecules are in constant or random motion, and this means they frequently collide. The collisions are elastic, and this means that there is no loss of energy, but instead, the energy is transferred from one molecule to another. This means in a given sample, at a given temperature, molecules will have a spread of energies about a most probable kinetic energy. Okay, so this is my diagram, and we have on the x-axis we have kinetic energy, and on the y-axis we have the number of molecules. So the area under the graph represents the total number of particles in the sample. So there are a few specific points we need to note about this diagram. Okay, so the first thing is that the graph always has to pass through the origin. So the reason the graph always has to pass through the origin is because that no particle ever has zero energy. The next important part of the curve is at the peak, and this is known as the most probable energy. So what the probable energy indicates is that most particles have energy around this value at any given time. The next point we have is the average energy, which is quite close to the most probable energy. So the average energy basically means that the area on both sides should be equal, so that the number of molecules with energy are equal on both sides. Okay, so the next part of the diagram we need to look at is this part, which is the asymptote. The graph always ends in an asymptote because there's no limit to how high an energy these particles can have. Last but not least, we have point number 5, which is going to be the activation energy. So the area above the activation energy, which I'll shade in for you. So this area represents the number of particles with at least this energy, which basically means energy is bigger or equal than the activation energy, so they can react. Okay, so now we can look at how changes in conditions changes the Maxwell-Boltzmann curve. The first condition we can change is temperature. So if I increase the temperature, the curve will shift to the right, but it will still start at the origin and only pass the original curve at one point. As you can see, the curve shifting to the right has increased the most probable energy and also increased the average energy. So now we can see why increasing the temperature increases the rate of reaction. This is because the area under the graph with an energy greater than the activation energy has increased. This means that more collisions will end up as successful collisions. So therefore, lowering the temperature has the same logic. It shifts the curve to the left, the most probable energy and average energy decrease, and the area under the graph with energy greater than the activation energy has decreased, so less successful collisions. You can also see that the graph is higher. This is because the area under the graph has to be the same because the number of particles don't change. So as you can see, changing the concentration means that the shape of the distribution is still the same, but increasing the concentration will increase the height of the graph. This is because there are more particles, so therefore you need to double the area underneath the graph. Doubling the height means that there is more particles underneath the graph with an energy greater than the activation energy, because the area under the graph is greater. Okay, so same logic for decreasing the concentration. You will halve the area under the graph because you're halving the concentration of particles. Therefore, a smaller area means less particles with an energy greater than the activation energy, so less successful collisions. Remember, both graphs still are asymptotes and pass through the origin. Okay, so lastly we see how a catalyst affects the distribution. As you can see, it's still the same curve. However, adding a catalyst will lower the activation energy, and so you get a bigger area under the graph that has an energy bigger than the activation energy compared with the previous. Okay, so this is the end of the revision video. Thanks for watching, I hope it helped, and good luck with your exams.